Weslake is a 100-year-old UK company with a rich heritage of developing powertrains. For the last 20 years, we've been manufacturing and designing an opposed piston engine for the purpose of replacing gas turbines, which are extremely expensive to purchase, very expensive to run, and very difficult to maintain. We're also replacing large displacement petrol engines using 100-octane leaded fuels. The purpose of the project was to remove mass and reciprocating weight from the engine. Our partner, Materion, which have developed a metal matrix composite which has extremely good fatigue properties at elevated temperatures. We've used this to replace the heavy steels that we have to use in our design of the engine. Our other partner was EFI. They were able to develop the electronic systems that we needed to be able to measure the efficiencies that we gained from this project. The technology of the opposed piston uniflow engine is we have two crankshafts geared together and two pistons coming together in a common combustion chamber. This results in a very lightweight engine with very high thermal efficiency, unlike any other conventional combustion engine available at the moment. The opposed piston uniflow engine has a hot cycle, making it extremely suitable for use of biofuels, SAF, sustainable aviation fuel, and other alternatives. It's already up to 50% more fuel efficient than current gas turbine technology and can reach the 2050 ATI goal of a 50% reduction in CO2 and 90% reduction of nitrous oxide gases.
This is the dynamometer test room. As you can see, there's much instrumentation on this engine here, our development engine here. We have the latest electronics units, most of it designed in-house, so we can control fuel injection, timings, pressures, injection duration at any speed and any load, engine load. We monitor all pressures, temperatures throughout, flow, anything we possibly need. We generally design and incorporate into our system ourselves. The monitoring system is held the other side of this bulletproof glass so that we can monitor it at all time, and we have full data logging as well. So we record the information and check it all out later on. This engine was used for development of part of the NATEP project. We were experimenting with exotic materials for piston design and cooling. Yes, it proved to be pretty successful, really. The idea was to reduce some weight from the engine, the reciprocating weight, the pistons going backwards and forwards, and made a simpler design. It was using a metal matrix type material, and NATEP helped us out with the funding of that project. This engine here, as you can see, is very small. Weslake originally looked at making four-stroke engines, which is our bread and butter business for many years, but we found a two-stroke diesel was a far lighter and a simpler way of doing it. It fits within existing aircraft cowlings because this is the typical layout. V engines and inline engines have too high a frontal area. This actual layout is exactly as you would have it in any light aircraft, whether it's a Cessna or whatever. You can see how small it is. This is an 80 horsepower engine. We also do up to 115 horsepower with the addition of a small turbocharger on this engine. Plus we intend to do a 3-cylinder version, which is 6 pistons, which will be up to 170 horsepower. And the weight of it will be sub 100 kilos, which is very light for a diesel stroke Avtur engine.
We see this engine development as a transition technology, and it's the most efficient powertrain available at the market and is available for marine and general aviation applications, and will fill the gap between electric and hydrogen developments, which still have some time before they mature and become useful forms of power. The global requirement in both marine and aerospace applications for this powertrain is absolutely immense. It's our intention to manufacture it in the UK, which will require skilled jobs and provide UK added value. The NATEP project gave us the confidence to undertake high-risk development work, which turned out very successful. Winning the award gave the credibility that we needed to attract further investment.
This project supported Weslake in developing the opposed piston uniflow powertrain that you see behind me. This project is very close to my heart because I was involved from the very beginning, helping Weslake to develop the application. I'm happy to say that most projects that get through the application process and get through to funding are successful. I'm particularly pleased that this project with Weslake has been highly successful, and it looks to me that Weslake and its partners have a very successful future in front of them.